Before we consider timing, let's remember how digital systems are normally used. They are used to process sequences of numbers. So numbers come in separated by the rising edge of a clock going through a flip-flop. If these numbers come from the outside world, we need to use a double flip-flop synchronizer for a single bit and some more complicated scheme for multiple bits. Anyway, the numbers come in through a flip-flop. This flip-flop could be the output flip-flop of some previous calculation if it's internal to our circuit. Then it goes through some combinational logic. For example, if we denote the input value by x, this combinational logic circuit might be computing x squared, and then we put it through an output flip-flop to make sure that the output here doesn't contain any glitches. Another example is a finite state machine that computes, for example, the cumulative sum. So I've got numbers coming in. For a finite state machine, I need to have my flip-flops to contain the current state. The output of the current state goes through some combinational logic to form the output. It also gets fed back and goes through some combinational logic to determine the next state. And the next state is also influenced by the input here. So again, I find that in my circuit that processes numbers, I have got flip-flop going through combinational logic into another flip-flop, flip-flop through combinational logic into another flip-flop. And tangentially, I don't have to be processing numbers like this. I might have a finite state machine that controls traffic lights, where the input are different sensors from the road and pedestrian crossings. The finite state machine works out how long the traffic lights have been red in one direction, green in another, and the output of the finite state machine determines what color the various traffic lights are. Whatever circuit we have, it looks like flip-flop going through combinational logic, going through another flip-flop, going through combinational logic, going through another flip-flop, etc. Now, there might be a feedback loop, so this flip-flop might be the same as this flip-flop, but it doesn't matter. We can pretend they're two different flip-flops if it makes it easier for us. One way of understanding this by way of analogy is to think of an assembly line. So maybe we are making hamburgers. The fresh ingredients come in at the start here. This worker here might put butter onto the bread. This worker here might add the little hamburger meat in there, and so forth. Different parts of the assembly line do different things. If you like, it's a car assembly line with a conveyor belt. Car parts come in, this worker adds a steering wheel, this worker adds some wheels, etc. What moves the conveyor belt in terms of our digital system? Well, at the rising edge of the clock, the conveyor belt moves everything one unit to the left, so to speak. So with our system up here, if the first number comes in is 2, then when there's a rising edge, this 2 gets copied to the input for this worker to do something. When this worker's finished doing the computation, the number at the output here is ready for the next rising edge of the clock for this flip-flop to move it on to the next worker, and so forth. So just like an assembly line, numbers come in, they get processed at each stage, and then they move along to the next stage. For timing to work then, we see that the clock period, which is the time between two rising edges of the clock, that's the clock period there, this clock period has to give each worker enough time to do his or her job. So if this worker requires 10 milliseconds to compute the correct answer, and this worker requires 5 milliseconds to compute the correct answer, there's no point clocking this at 5 milliseconds, because even if this worker could just keep up, the assembly line will be moving on before this worker has had time to finish computing the correct answer, and so it's not going to work. So the clock period must be longer than the time it takes the slowest worker to process the data. That's rule number 1. Rule number 2 is a little bit harder to explain by analogy, but it's as if we want to make sure that the conveyor belt moves just 1 unit to the right and it doesn't skip and move 2 units. Specifically, rule number 2 for timing, we can come back to our shift register. And remember, when we discussed our shift register, we wanted to make sure that at the rising edge of the clock, the second flip-flop takes a photograph of the old value at the output of the first flip-flop. So what can go wrong is if at the rising edge of the clock, the first flip-flop changes its output too early before the second flip-flop has had a chance to photograph it. That's akin to the assembly line moving along 2 places rather than 1. So there are actually only 2 rules in order to get timing correct. The first rule says that the clock period has to be sufficiently slow so that every worker has got time to process the signal. Rule number 2 says that the output of a flip-flop and correspondingly the output of the combinational logic, they cannot change so fast that the next flip-flop hasn't had a chance to photograph the previous output. That's rule number 2. Provided rules 1 and 2 are satisfied, our circuit's going to work. And remember, for this course, we are only considering circuits where every flip-flop is clocked by the same clock. This is known as synchronous design, and it's surprisingly general in that almost all circuits can be built using this principle by utilizing some clever tricks every now and then. To make sure that rules 1 and 2 are satisfied, we need to understand the timing of combinational logic and the timing of flip-flops. In particular, for the combinational logic, we need to know when the input changes, and there's a transition at the input, when does the output first start to change? That affects rule number 2. You see, if the input changes and somehow almost immediately the output starts to change due to a glitch, and this flip-flop's connected to the output here, this flip-flop might not have had a chance to photograph the old output before the new output came there. So it's important to know how long before the output of combinational logic starts to change when the input changes. The longer that is, in a sense, the better, because it gives the following flip-flop enough time to photograph the output. This delay that I was just talking about is called the contamination delay. So the contamination delay is a promise. If the contamination delay is 2 nanoseconds, it's a promise by whoever made this combinational logic that if the input changes, the output will not change until at least 2 nanoseconds later in this example. Now, it might change later than that. That's okay. In fact, we can never compute the contamination delay perfectly because it's influenced by temperature. It can be influenced by the exact combinations of the different inputs coming into the combinational logic circuit and so forth. We need simple design rules. We need simple models, and a simple and standard model for combinational logic is that the combinational logic, if the input is constant, of course the output's going to be constant. It's given by a truth table. As soon as the input changes, what our simplified model says is that the output is going to stay constant for a certain period of time. Then it's going to do who knows what. There might be glitches present and whatnot. And then after another period, we're going to have the correct answer. This is what our simple model says. And the first part, the time when we guaranteed that the output will not change, is called the contamination delay. The time it takes until we get the correct answer is known as the propagation delay. Of course, the propagation delay needs to be greater than or equal to the contamination delay. Otherwise, it would make no sense. We do not add the two. The two start counting as soon as the input changes. So if the input changes at time t equal to 0, then the output is going to remain constant until at least, in this example, 2 nanoseconds has passed, because that's the contamination delay I'm using here. After 2 nanoseconds, and before the propagation delay, which we will say is 5 nanoseconds here, we don't know what will happen at the output. The output might stay constant for longer. It might have some glitches. It might end up with some voltage halfway between the input and the output. We don't know. But what we do know is that at t equals to 5 nanoseconds, so to emphasize, this is counted from when the input changed at t equals to 0. We do not add it to the contamination delay. Once the propagation delay has gone past, we know that the output is the correct value as given by the truth table for this combinational logic. Again, propagation delay is not going to be exact. We can't compute it exactly because it depends on the temperature, the previous inputs, the type of transition, etc. But it's a promise. It says that maybe the output is ready sooner, but I guarantee you that after 5 nanoseconds, the output is going to be correct and it's not going to change again. Just to remind you how these concepts fit in, remember we said we have got two properties that we want to hold if this circuit here is going to work, this pipeline segment. We need to make sure that at the rising edge of the clock, the output of this flip-flop doesn't zoom through this combinational logic too quickly and change the input to the second flip-flop before it's had a chance to photograph the input. That is why the contamination delay is relevant. It gives us more time for the second flip-flop to photograph the correct value here, the old value we want. The propagation delay concerns the first property. The first property is that our combinational logic has to have finished doing its job before the next rising edge of the clock. So at the next rising edge of the clock, at the first rising edge of the clock, the next value gets loaded in at the front of this combinational logic. In terms of the assembly line, the hamburger has moved across, ready for tomato to be put on it. The worker has to have finished processing this number, putting the tomato on the hamburger, before this flip-flop takes a photograph at the next rising edge. So the time it takes to process is given by the propagation delay. And that's why contamination delay and propagation delay are important when trying to figure out if this circuit here is going to work. Let's now look at the flip-flop. The flip-flop is going to have not 2, but 4 numbers associated with it, concerned with timing. Now, the textbook calls 2 of these numbers differently from how I'm going to call them. I'm going to call 2 types of delays with the flip-flop the same as for combinational logic. Now, that doesn't mean that there is any connection between a flip-flop and a combinational logic circuit. They are different elements, so to speak, but hopefully this makes life a little bit easier for you rather than a bit more confusing for you. So there's contamination delay, and for a flip-flop, I'm going to define it as, and it's measured from the rising edge of the clock, and we look at the output, so D's in, Q's out. When there's a rising edge of the clock, this flip-flop is going to photograph its input, and it's going to pass that photograph onto its output Q. But it's going to take time to do that. So the output of this flip-flop just after the rising edge is going to be the same as what it was just before the rising edge, because we have a contamination delay normally with a flip-flop. If the contamination delay is 2 nanoseconds, that means that the output of my flip-flop is guaranteed to not change within 2 nanoseconds of the rising edge. There's then, of course, going to be a propagation delay. And if the propagation delay is 4 nanoseconds, that means that 4 nanoseconds after the rising edge of the clock, the output is guaranteed to be correct. So it's the same principle as for combinational logic. It's just I'm taking the input, in this case, to be the rising edge of the clock. That's when the delays start to get timed. So to summarize, when there's a rising edge of the clock, the output of my flip-flop is not going to change until the contamination delay period has expired. After the contamination delay period has expired, the output could do anything. It could oscillate, it could do whatever it likes. This is a crude model. We don't care what it does. All we do care about is knowing that there's going to be some other period, in this case 4 nanoseconds. 4 nanoseconds after the rising edge of the clock, we are guaranteed that the output of the flip-flop is going to be correct. Same principle as for combinational logic. The output doesn't change for at least this amount of time, and the output is going to be correct before this time has elapsed. These times can't be known exactly, they are just promises. The flip-flop promises not to change its output within 2 nanoseconds, and it promises to have the correct output after 4 nanoseconds in this case. If we look at our simple shift register from before, we can now understand what we want to happen. We want the second flip-flop to take a photograph of the old value. That's why this contamination delay is so important, because there's a rising edge of the clock. The first flip-flop takes a photograph of its input, but it does not change its output until after the contamination delay period has expired. And this is what gives the second flip-flop a chance to take a photograph of the old value before it gets replaced by the new value. Here, in our shift register, the relevance of the propagation delay is that I cannot clock my shift register arbitrarily fast. It takes time for this flip-flop to take a photograph of its input, and if I try to clock this too fast, then these flip-flops can't keep up. They're busy taking photographs, but they don't have enough time to update the output with the new photograph. So for this circuit to work, the clock period has to be slower than at least the propagation delay to give each flip-flop enough time to take a clear photograph and pass it on to the next flip-flop. Our humble flip-flop, in addition to having a contamination delay and propagation delay, and remember those terms are non-standard, the concept is entirely standard, but the book calls them by different names. I like to call them contamination delay and propagation delay nonetheless. The flip-flop has got two other numbers associated with it, and they relate to avoiding metastability. Remember, we have emphasized that the input must be constant at and around the rising edge of the clock. The analogy is, if someone is trying to take your photograph, do not move around or the photograph will be blurry. For the flip-flop, if the input changes too close to the rising edge, the output might get stuck at not a logic 0, not a logic 1. The output might get stuck halfway between a 0 and a 1. Now, This is an unstable state, so within a relatively short period of time, on average, the output is then going to choose either a 1 or a 0. We don't know which one. We don't know how long we're going to wait. In theory, you could wait forever. In practice, you don't wait very long at all. But regardless, we want to avoid this metastable state if at all possible. When crossing clock domains, we can't avoid it. But if we're within our own circuit, we can most certainly avoid it, because within our own circuit, we've got a flip-flop, combinational logic, another flip-flop, and this flip-flop, the first one, controls when data is released to the worker, this combinational logic, and that determines when the output here is going to change and when it's going to be ready. Intuitively, we now know that this output will first change according to the contamination delay of both this flip-flop and this combinational logic. Don't worry, I'm going to cover that in greater detail later, but intuitively we understand now that contamination delay determines when the output first starts to change. After the rising edge of the clock, we also have a propagation delay, which tells us when the output here has reached its correct value. And so we now know the time when the input to the second flip-flop, we know the time between which it's changing and when it's the correct value. And so provided we take a photograph when it's at the correct value and is not changing, we are guaranteed to avoid metastability. And that's all timing is about. That's all it is. We just have to make sure that to avoid metastability, we just have to make sure that the input to this flip-flop here does not change too close to the rising edge of the clock. The only other thing we have to worry about is giving the worker enough time to have come up with the correct answer before this flip-flop starts taking a photograph. Okay, so we need to ask the flip-flop manufacturer, how can we avoid metastability? And the flip-flop manufacturer is going to give us two numbers. One's going to be called the setup time, and one's going to be called the hold time. And again, like contamination and propagation delays, these are just promises. They are not exact numbers, but they are guarantees. So if the setup time is 1 nanosecond and the hold time is 2 nanoseconds, all this means is that we look at a rising edge of the clock. For the setup time, this refers to just before the rising edge of the clock. So we go 1 nanosecond before the rising edge of the clock based on the setup time. And the hold time refers to the time after the rising edge. So in this case, I look at 2 nanoseconds after the rising edge. So 1 nanosecond before the rising edge and 2 nanoseconds after the rising edge of the clock, if the setup time is 1 nanosecond and the hold time is 2 nanoseconds. Within this period, 1 nanosecond before, 2 nanoseconds after the rising edge of the clock, I must have the input to my flip-flop constant. If the input to my flip-flop is constant between the setup and hold times, then I'm guaranteed to avoid metastability. The flip-flop manufacturer has told me that in the datasheet. So how does this work in practice? Well, remember, we have a flip-flop, we have combinational logic, we have another flip-flop here, and there are two things that we need to ensure. The first thing is that the clock period is sufficiently slow that the worker has had a chance to compute the correct output before the second flip-flop takes a photograph of it. The second thing we have to make sure is that at the rising edge of a clock, the input here doesn't cause the output to change too soon, which then when it goes through the combinational logic also doesn't cause the output there to change too soon. And in other words, we don't want the input to this flip-flop to change too close to the rising edge of the clock to cause metastability. So for point 2, we just need to make sure that the contamination delay is sufficiently big. In this case, contamination delay is a good thing. We are now able to compute whether or not these two conditions hold from the numbers we're given. Remember, for this flip-flop here, I have got the contamination delay and I've got the propagation delay. They're given to us in the data sheet. Similarly, for this combinational logic, I know it's contamination delay and it's propagation delay. So for example, if this flip-flop here had a contamination delay of 1 nanosecond and this logic circuit here had a contamination delay of 3 nanoseconds, what this means is that at the rising edge of a clock, there's going to be at least 1 nanosecond before this starts to change, and then at least another 3 nanoseconds, or in other words, 4 nanoseconds after the rising edge of this clock is going to be the first time that this output starts to change. And so, roughly speaking, provided this flip-flop is able to photograph its input within 4 nanoseconds of the rising edge of the clock, then everything will be fine. Now, to be precise, when must this flip-flop take a photograph? Well, that's what the setup and the hold time are telling us. And I'll cover this in part 2 in more detail, but intuitively, if we find that our contamination delay is 4 nanoseconds, then provided the hold time of this flip-flop is less than 4 nanoseconds, then we are in business. It means that this flip-flop can take a photograph of the input and not have to worry about it changing too soon. That determines whether our second constraint is satisfied or not. For our first constraint on the clock period, well, this relates to the propagation delay. There's a rising edge of the clock. The new hamburger comes in, being presented to this worker. How soon does this worker get to see the new hamburger? Well, it has to first propagate through this flip-flop. So if the propagation delay of this flip-flop were 3 nanoseconds, then 3 nanoseconds after the rising edge of the clock, this worker has got all the parts he or she needs to process the hamburger. So we've got 3 nanoseconds through the first flip-flop. In other words, it takes the conveyor belt 3 nanoseconds to move all the parts along to the next worker. Then this worker is going to take, if the propagation delay is 10 nanoseconds, it means that this worker requires 10 nanoseconds to get the right answer once its input is correct. So there's a rising edge of the clock. 3 nanoseconds later, the input to the combinational logic is correct. So another 10 nanoseconds later, in other words, at 13 nanoseconds after the rising edge of the clock, this output is going to be correct. Now, if this flip-flop took a photograph at precisely 13 nanoseconds after the last rising edge of the clock, in other words, if the clock period is 13 nanoseconds, this design might not work, because remember, this flip-flop has got a setup time. Its input must be ready before the photograph is taken. How much before? That's what the setup time tells us. So if the setup time is 1 nanosecond, it means that the input to this flip-flop must be ready 1 nanosecond before the next rising edge of the clock. So there's a rising edge of the clock. It takes us 13 nanoseconds for the correct answer to arrive at the input to this flip-flop. I need an extra nanosecond for the setup time. So in other words, provided the clock period is greater than 14 nanoseconds, then my design should work from that perspective. Why greater than and not greater than or equal to? Because nothing's perfect. You need to leave engineering margins for things to work. This, by the way, shows that we can't have circuits operating at arbitrarily high frequencies. That should make sense. Your computer's not clocked at a terahertz. It's limited to a few gigahertz because there are fundamental limits. The fastest we can clock our circuit is known as F max. In our case, we found that F max is 1 on 14 nanoseconds. It's whatever frequency has got the period of 14 nanoseconds. If we were to clock our circuit any faster than Fmax, then the worker will not have had enough time to compute the correct output, and our design might not work. Now I say might not work because all these delays are just promises, they're just approximations. Now they're not approximations in that they might be right or wrong, it's just that they err on the side of safety. If the propagation delay is 5 nanoseconds, it doesn't mean we have to wait 5 nanoseconds, it simply means after 5 nanoseconds we are guaranteed to get the correct answer. So if you're lucky, your design might work at or above Fmax, but you can't guarantee it. If the temperature changes, it might stop working, etc. In other words, you'd be leading a dangerous life. To summarize, digital circuits look like output of a flip-flop going through combinational logic, going into the next flip-flop. We think of this as an assembly line. Each combinational logic circuit represents a worker. At the rising edge of the clock, the assembly line moves over to the next worker. They all need to process it. There are two constraints that need to be satisfied for the timing to be correct. The conveyor belt can't move too quickly, so to speak, and this relates primarily to propagation delay. Every worker has to have enough time to process the data before the next flip-flop photographs it. The second constraint has to do with making sure that the input to a flip-flop doesn't change too close to a rising edge of the clock due to glitches and so forth, meaning that when the output of the first flip-flop changes, there might be some change that occurs very soon after. It won't be the correct answer, but some change might occur. That relates to the contamination delay. To make sure that a flip-flop does not enter a metastable state, then we need to make sure that its input is constant, starting from the setup time minus when the rising edge occurs to the hold time after the rising edge occurs. So if the rising edge occurs at time t equals to 10 nanoseconds, and the setup time is 1 nanosecond, and the hold time is 2 nanoseconds, that means that from 9 to 12 nanoseconds, the input to this flip-flop has to be constant. If it is, we are guaranteed to avoid metastability. And that's it for part 1.